This is the 10th session in our Decision Tree series. Today, continuing from the previous video, we're going to walk through cost complexity pruning on a cart decision tree, step by step, with a concrete example. In the last video, we focused on the key ideas and formulas behind cost complexity pruning. So in this session, our goal is to take those formulas and actually apply them. Let's start with a simple tree and see how pruning works in practice. First, recall that the cost complexity of a single node T is defined as the misclassification cost plus a penalty term. Since a single node is also a leaf, the number of leaf nodes is 1. So the penalty term simplifies to just alpha. For a subtree T, the cost complexity is calculated by summing the weighted misclassification rates of all leaf nodes, and then adding a penalty proportional to the number of leaves. We also define a value called alpha star. This is the value of alpha at which the cost of keeping a node as is equals the cost of expanding it into a subtree. Think of it as a measure of split efficiency. How much do we gain from this split relative to the complexity it adds? Since we already covered these formulas in detail in the previous video, let's focus here on how to put them to use. Let's start by computing the cost complexity for node T1. Node T1 contains 16 data points. The two classes are evenly split, so the misclassification rate is 8 out of 16. Since this node contains all the data, its weight is 1. So the cost complexity of node T1 is simply as follows. Next, let's look at subtree T1, which is obtained by splitting node T1. In this example, T1 is actually the entire tree, containing 4 leaf nodes. To compute its cost complexity, we take the weighted misclassification rate of each leaf and sum them up. Here, all 4 leaf nodes are pure, so their misclassification rates are 0. That means the total cost comes only from the penalty term, which is 4 alpha. Now, using these results, we compute alpha star for T1. The number of leaf nodes is 4. The error at node T1 is 8 out of 16. And the error of the subtree is 0. So alpha star for T1 is 1/6. Next, let's repeat the same process for node T3 and subtree T3. Node T3 contains 12 data points, with 4 belonging to the minority class. So its misclassification rate is 4 out of 12. Its weight is 12 out of 16. The subtree T3 has 3 leaf nodes, and again, all leaves are pure. So its cost complexity is 3 alpha. From this, alpha star for T3 comes out to 1/8. Running the same calculation for node T5 also gives us 1/8. Now, which split should we prune? Recall that a smaller alpha star means the split provides relatively little benefit compared to the complexity it adds. In other words, it's the least efficient split in the tree, and that's exactly what we want to remove. This least efficient split is called the weakest link. In this case, both candidates have the same alpha star, 1/8. When there's a tie, we typically prune the subtree with fewer leaf nodes. This is a common heuristic. When two splits are equally inefficient, we remove the simpler one, usually one that sits lower in the tree. At this point, you might ask, does the weakest link always end up being the lowest node in the tree? Interestingly, no, not always. Let's look at these two example trees. In the left tree, node T5 is the weakest link. But in the right tree, node T3 becomes the weakest link instead. So what makes the difference? It comes down to the misclassification rate at node T3. In the left tree, node T3 has an error rate of 4 out of 12, about 33.3%. In the right tree, it is 1 out of 8, about 12.5%. When T3 already classifies data this well, splitting it further adds complexity without much payoff. So that split is flagged as inefficient and becomes the candidate for pruning. And here's a useful implication of this. If a parent node is already identified as the weakest link, we can skip evaluating its child nodes entirely. This makes the pruning process more efficient by avoiding unnecessary computation. Now let's continue the pruning process. We remove subtree T5, the weakest link, which simplifies the tree from TA to TB. Node T5 is now a leaf. We then recompute alpha star values for the updated tree. This time, alpha star for T1 is 3/16, and for T3 it is 1/8. So T3 is now the weakest link. Pruning T3 gives us tree TC. We keep repeating this process. Each round removes one more split until we're left with just the root node, which we'll call TD. So we've now generated a sequence of trees, each corresponding to a different value of alpha. Smaller alpha values produce deeper, more complex trees. Larger alpha values produce simpler, shallower trees. These trees form our set of candidate models. In the final step, we use cross-validation to select the best tree among these candidates. And that's the core goal of cost-complexity pruning. Finding the tree that best balances accuracy and simplicity. Before we wrap up, there's one important point worth highlighting. In this example, we evaluated pruning at every node. But in practice, once a split is identified as the weakest link, all splits below it are automatically excluded from consideration. This means we don't need to explore every possible subtree, which significantly reduces the number of candidates and speeds up the entire process. So far, we've walked through the full procedure of cost-complexity pruning. In the next video, we'll bring this to life in code, using scikit-learn's decision tree classifier to implement everything we've discussed. See you there.